This is chapter 4 of Atoms and Elements. Section 7 is orbital diagrams and electron configurations. In the previous lesson, we introduced the idea of the electronic structure of the atom, and we talked a lot about electron energy levels and sublevels and orbitals, and how many electrons you can fit into these orbitals and sublevels and energy levels and things like that. And you're probably a little bit confused about what it all really means in terms of how you should think about the atom. When you first study this topic, there's a lot of strange information, and it doesn't really make a lot of logical sense the first time you talk about it. So in this lesson, I want to try and make that a little bit more concrete and think about what those energy levels and sublevels that we learned really means in terms of how an atom is built. Okay? And when I say how an atom is built, it's because I want you to think about it that way. I want you to think about starting from a nucleus, right, which is where all the protons and neutrons are, and then adding the electrons to the atom one by one. Okay? So for a simple atom like hydrogen, it's very easy. You have one proton in the nucleus. Most isotopes of hydrogen don't even have a neutron in them, so you just have a single proton with the +1 charge. And to make a neutral atom of hydrogen, all you have to do is bring an electron close to it and put an electron into the atom. And since you have only one electron in that atom, then that electron is going to get as close as it can to the nucleus. It's going to go to the lowest possible energy state, which is going to be in the n equals 1 energy level. And in the n equals 1 energy level, you'll remember there is an s sublevel, which is just a single orbital. Okay? So you can see that down here. The lowest energy that an electron in an atom can get to is the 1s sublevel. Okay? That's a very simple atom. It's really just a proton with an electron orbiting around it. Okay? The next simplest atom is helium. Helium has 2 protons in its nucleus with a +2 charge, and so you need to put 2 electrons into helium in order to get a neutral atom of helium. So again, when you start from the nucleus, you add the first electron and it goes into this 1s orbital. And then when you add the second electron, because an orbital can hold 2 electrons, it also goes into the same 1s orbital. Okay? After that, it can start to get a little complicated, because in the next row, then you have 1s and 2s orbitals, and you're adding more electrons, and so we need to understand the rules for sort of filling these electron orbitals. Okay? So to begin with, the electron energy levels have a certain order. We've talked about the order or the energy levels themselves, right? They start at the lowest, the n equals 1 energy level, and the next highest is n equals 2, etc., etc. And then within an energy level, the sublevels also have slightly different energies, and so they're ordered from S at the lowest energy to P, and then D, and then F, and then beyond that, there's not really anything we're going to need. Okay? So this is how the rules begin for filling an atom with electrons, right? All of the electrons go into the atom and they go to the lowest energy level that's available to them. Okay, so the first electron is always going to go all the way down to the 1s orbital because that is the lowest energy orbital in any atom. Okay. Once you start filling these orbitals up, however, you're using up the orbitals, and you have to then put electrons into higher energy orbitals, right? Or an orbital can't just hold as many electrons as you want to put in it. Okay? So on the right-hand side here, we see sort of a reproduction of the diagram we saw in the last slides, but now the energy levels are, the sublevels are also ordered in terms of their energy. And we see that the order is not as clear as it was before. So you start with the 1s, right? You start with the 1s orbital, and then you go up to the 2s orbital. And then after 2s, you have another sublevel in the n equals 2 level, and that's the 2p orbital, right? And so then that's your complete n equals 2 energy level, and so then you go to the n equals 3 energy level, and you start back with a 3s sublevel, and then after s comes the 3p sublevel. And then there should be a 3D sublevel, right? Because n equals 3, so there are 3 sublevels, so you have S, P, and D. But it doesn't go directly to the 3D sublevel after 3P. Instead, the 4S is actually a little bit lower in energy than the 3D. And so the next electrons you go to after 3P go into the 4s orbitals. And then you get to the 3D orbitals finally, right? Before you go on to 4p, you get the 3D orbitals here. And then you go to 4p, okay? But then again, before you get to 4D, it doesn't go that way. It goes to 5s, and then then it goes back to 4D, and then it goes to 5p. So it gets a little complicated around here. Okay? You don't need to memorize this chart. What we're going to learn in this lesson, one of the things we're going to learn in this lesson is how you can actually use the periodic table itself to reproduce a lot of this information and to figure out a lot of this ordering of the electrons in an atom. You may also be wondering at this point why orbitals can only hold a certain number of electrons and why all of the electrons can't just go to the lowest energy state in an atom. Okay? In some physical systems, you can put all of the particles into the lowest energy state and it's not a problem, but that's not the case for atoms. And so the reasons have to do with some complex quantum mechanics, and we're not really going to get too much into that, but I do want to talk about this idea of orbital capacity and how orbitals can only hold a certain number of electrons and why. And so that really begins in the early days of quantum mechanics with an Austrian physicist named Wolfgang Pauli, who studied the structure of atoms. And what he discovered was that there's this general principle that no two electrons can be in the exact same state. Okay? The state meaning the exact same configuration with the exact same energy. But we know that an orbital, which is an energy configuration, can hold two electrons. So in order for the Pauli exclusion principle to apply, there must be some other property of the two electrons in that orbital that is different between them, that distinguishes between the two. Okay? If there wasn't, then they would be in the same state, which would violate the principle. So since they're in the same orbital, they have to have something else that's different. And it was discovered experimentally that electrons actually carry a certain amount of angular momentum, or what we call spin. So this was then thought to be the property that distinguishes between the electrons in an orbital. Okay? You can have the orbitals spinning either clockwise or counterclockwise. Right? They can't just spin in any direction, but they can spin one way or the opposite way. And so we characterize these as spin up. One direction is spin up, and one is spin down. Okay? And we just usually denote them by an arrow pointing up and an arrow pointing down. Okay? Which way is clockwise and which is counterclockwise is pretty arbitrary, and we don't really need to worry about that. But the idea is if you have two electrons in an orbital, in order for them to be different, one has to be pointing up and one has to be pointing down. They cannot both be pointing in the same direction. It's impossible. Okay? And if it's a little bit strange for you to think about thinking of a spin in terms of just an arrow pointing in some direction, you can just imagine it like a screw, right? Imagine you're screwing a screw into a piece of wood. If you turn the screw clockwise, it'll go into the wood. If you turn the screw counterclockwise, it'll pull out of the wood. Okay, so you can characterize that direction of spin by just a single arrow pointing in one direction. Okay? And so this is really the reason that an orbital can only hold two electrons at most. Okay? And that determines the orbital capacity for the orbital and thus for the sublevel and the energy level and so on. So that brings us to the idea of orbital diagrams. Okay? If we want to know how the electrons are arranged in an atom, we can start to look at lists of the orbitals that are available and then fill them with electrons. Okay? Like I said in the first slide, you can imagine starting from a nucleus that has no electrons, and then you add the electrons in a certain order, and they go into certain orbitals in a specific order. Okay? So in an orbital diagram, we represent the orbitals by boxes, right? We've seen this before. Each of these individual boxes is an orbital, right? So this is an orbital, this is an orbital, this is three orbitals that are stuck together because they're all part of the 2p sublevel, and so on. This is 5 orbitals that are in the 3d sublevel, okay? So the boxes, which are orbitals, are grouped according to their sublevel and then according to their energy level, okay? And remember, each box, well, each orbital, can only hold at most 2 electrons, and we represent the electrons by their spin, which can be either spin up or spin down. Okay? So an orbital can have an up arrow and a down arrow, and that is all it can have. It can never have 2 up arrows, and it can never have 2 down arrows, and it can certainly never have more than 2 arrows. The best way to really understand orbital diagrams is to just jump right into an example. So let's think about the nitrogen atom. Nitrogen is a very important element. It accounts for a large part of our body mass. It's found in amino acids, proteins, nucleic acids, all sorts of things in your body. So it's an atom, an element that we're going to come back to very frequently in this class. So how do we draw the orbital diagram for nitrogen? Well, the first thing we need to know about nitrogen is how many electrons it has. Okay, so to think about that, we need to first know nitrogen's atomic number. If you look in the periodic table, nitrogen has an atomic number of 7. That means it has 7 protons, and so a neutral atom is also going to have 7 electrons. Okay, so we can begin by just sort of drawing the first few boxes, the first few orbitals corresponding to the n equals 1 energy level here, and then the n equals 2 energy level here, which consists of 2 sublevels, the s and the p. Okay? So we can start from this, and then if we need more room, we'll add it later. Okay? And so what we're going to do is we're going to start to fill these orbitals in order with the 7 electrons that nitrogen has. So the first electron, like I said, for hydrogen, the first electron goes to the 1s orbital because that is the lowest energy orbital in any atom. Okay, so the first electron that goes into nitrogen, okay, remember you're imagining that you have a nitrogen nucleus, which is just 7 protons and some neutrons. We don't care about those, but you have a nucleus of 7 protons, and you're adding the first electron to this atom. And so the first electron is going to go as close to the nucleus as it can get, and that is going to put it in the 1s orbital. Okay. Then you have another electron that you can put in because you have 7 to put in total. So after the first, you have the second one, and the second one is also going to go into the 1s, but it's going to adopt the opposite spin, right? But they can both fit into that 1s orbital very close to the nucleus because they can take on opposite spins. So we fill the first orbital, the 1s orbital, with 2 electrons. Okay, this is the n equals 1 energy level. So at this point, we've actually filled the entire n equals 1 energy level. But we still have 5 electrons left, right? Total of 7, we've placed 2, so now we have 5 electrons left, so the next electron is going to go into the next highest energy level. We completed n equals 1, so now we're going to go to n equals 2. And in the n equals 2 energy level, they're going to again go to the lowest sublevel. So the sublevels always start at s. So this electron, the next electron, the third electron, is going to go into the 2s orbital. Okay? And then we can put another electron in, the fourth electron, and that will also go into the 2s orbital because it can hold 2. It'll just adopt an opposite spin. Okay? So now we have the 2 electrons in the 1s orbital and 2 electrons in the 2s orbital. But because the n equals 2 energy level has 2 sublevels, we also have 2p sublevels that we can still fill, right? So we've accounted for 4 electrons so far. Out of the total of 7, that means we have 3 electrons left. The 3 electrons that we have left are clearly going to go into the 2p sublevel. The 2p sublevel has 3 orbitals, which means it can hold 6 electrons. So there's plenty of room in the 2p sublevel to hold those last 3 electrons of nitrogen. But these electrons are also going to go in a certain way. They're going to arrange themselves in a certain way. It helps to remember that because electrons are all negative, they tend to repel one another. Okay, two negative electrons are not going to want to come close to one another. Okay, so they're going to spread out within the sublevel as much as possible before they begin to bunch up or double count any orbital. Okay, so electrons don't really want to go into the same orbital unless they have to, unless it's very energetically favorable for them to. So the 2s sublevel fills with 2 electrons before the 2p because the 2s sublevel is lower in energy, right? If you remember that diagram from a few slides ago, we started with the 1s, and then above the 1s is the 2s, and then above the 2s is the 2p sublevel, right? So this is in terms of energy. We go to the lowest box first and we put 2 electrons in, and then the next highest we put the next 2, and that's why the 2 go in there, right? They repel one another a little bit, and so you might think that they would go, one of them would try to go to the 2p orbital, but because the 2s is lower in energy, they both go in there. And only after the 2s is filled do the next electrons start to go into the 2p sublevel, which is what this is, okay? But again, because they all repel one another, they spread out as much as possible, and they go into different electron orbitals. Okay? And the other thing to remember is that when you have multiple electrons in separate orbitals within a sublevel, like these, they tend to align or point in the same direction. Okay? So electrons within a single orbital point in opposite directions. But if they're all in separate orbitals in the same sublevel, then they tend to point together. Okay? So this is now accounting for 1, 2, 3, 4, 5, 6, 7 electrons, which is all the electrons that are needed for nitrogen, for a neutral atom of nitrogen. So this is the completed orbital diagram for nitrogen. It shows you which orbitals the 7 electrons sort themselves into, just based on their energies. So we can take this orbital diagram and we can actually write it in an even more compact form called the electron configuration. In the electron configuration, we don't want to have to worry about drawing little boxes and arrows anymore. So we're just going to identify the different sublevels and then specify how many electrons are in each of them. Okay? So we still write them in the same order as before, which again, we'll get to a way to remember that order better using the periodic table. But you write them in the specific order that they show up in, and then you write the number of electrons as a superscript. Okay? So the number followed by the letter here indicates the energy sublevel. This is n equals 1 and an s sublevel. And then the number, the raised number, the superscript number, tells you how many electrons are in that orbital. So the 1s orbital was holding 2 electrons, so this is a 2. The 2s orbital also holds 2 electrons, so this is a 2. The 2p orbital for nitrogen, we're still talking about nitrogen now, holds 3 electrons, and so this is a 3. Okay? So this encapsulates a lot of the same information as the orbital diagram in a more compact space. So now we're going to look at how you can interpret the periodic table in terms of these electron configurations, right? So remember, the periodic table lists all of the elements from 1 all the way up to 118, and they are in order of their atomic number, right? The number of protons. So before we get into it, the first thing to notice about this is a little bit different in that this is helium right here. So the helium has been moved over from being part of the noble gases over to the other side of the periodic table here to bring it into what we're going to call the S block. Okay? And so we'll see that in a second why that makes sense. Right? So when you look at the periodic table, you count left to right and top to bottom, the way we normally would read. Right? So this is 1, this is 2, helium is atomic number 2, then down here you have atomic number 3, and then 4, and then you go across to 5, 6, 7, 8, 9, 10, right? And then you go down to the next row, which is 11, 12, you skip across, 13, 14, 15, 16, 17, and 18, right? And I'll stop there, but obviously it continues on, 19, then across. And so you're really counting protons in the nucleus. But because for the neutral atoms, the number of protons is also the number of electrons, you could also look at these numbers and think of them as the number of electrons that you need to place into that specific atom. So for instance, over here, we have carbon, which is atomic number 6. So for carbon, we need to figure out how to place 6 electrons into the energy levels we've been discussing to figure out its electron configuration. And so looking at the periodic table, the way it's written here is going to help us to do that because it separates it into different blocks depending on where the last electron went. Okay? So for all of these S blocks, okay, these yellow columns here on the left side, which are part of what we call the S block, the last electron that was placed in each of these atoms went into an S orbital. Okay, so for hydrogen, it went into a 1s orbital. For helium, it completed the 1s orbital. For this down here, lithium is number 3. The third electron in lithium also goes into an s orbital. It's a 2s orbital. And then beryllium, number 4, it also goes into an s orbital, but it's a 4s orbital. And then skipping over here, we see atomic number 5, which is boron. And so the last electron that goes into boron, or the highest energy electron in boron, is in the 2p orbital. And so it's a member of the p block. Okay? And since the p sublevel can hold up to 6 electrons, we have 6 columns in the p block. Okay? because the s sublevel is a single orbital and it can only hold 2 electrons, we only have 2 columns in the s block. Okay? And then we get down to the lower levels here, and you start to see that we have a d block, the 3d. And what you might notice is that the period is the same as the highest n value, except for these d block elements, right? So in each of these cases, the rho, or the period, is the highest value of the n, the highest energy level, or n value, for that electron configuration. So for instance, atomic number 11 here, right, the last electron in atomic number 11 goes into the 3s orbital. Okay, so rho 3 means the highest electron, the highest energy electron is n equals 3, and it being a part of the s block means it goes into an s orbital. Okay, for the transition metals, this is shifted a little bit, and it's shifted because of that order that we saw previously on one of the first slides in this lesson, where after the 3p orbitals, instead of going directly to 3d, it goes to the 4s instead, and then after 4s, it goes back to the 3d. So the period is the same as the highest energy n value for the element, except for the d block, where it's offset by 1. It's 1 less than the highest energy level is 1 less than the period. So in the s block elements, the highest energy electron is in an s orbital, like we said. In a p block, it's in a p orbital, and so on. Since an s orbital can hold 2 electrons, there are 2 columns in the p block. There are 6 electrons in the p block because the p sublevel holds up to 6 electrons. Remember that there are 5 d orbitals in a d sublevel, so that holds up to 10 electrons, which is why the transition block, the d block of transition elements, is 10 columns wide. Okay, so you can really retrieve a lot of the structure, or interpret a lot of the structure, from looking at the periodic table in the right way. It's also interesting to note that there's a particular stability associated with a filled sublevel, especially a filled p sublevel. So starting in row 2, or period 2, you have p orbitals. Okay? In the first row, you only have the s orbital because it's n equals 1, so there's only one sublevel. And once you fill it with 2 electrons, like helium has, then there is stability for that, right? Helium is a very stable atom, and it's part of the noble gases. Okay? That's why it's placed on the right side in the typical periodic table, even though it's, according to the configuration, part of the s block. Okay? And then when you get down to period 2, then the stability comes after you've filled the 2p block, okay, at the end of the p block in period 2. Okay? So that last group, that last column of every period in the periodic table, is the noble gases. It's elements that have a filled s and p sublevel, and therefore have a particular stability. They're not going to react very strongly with anything else. In fact, most of those elements hardly react at all. And so that allows us to get to the idea of core electrons versus valence electrons. Okay? So again, remember that the chemical and physical properties of an atom are determined by its electron cloud. And in fact, they're really determined by the outermost electrons. Okay? So those electrons are particularly important, and we give them a name. We call them the valence electrons. Okay? So the valence electrons are the electrons that are in the highest energy level of the atom that you're talking about. Okay? They have the highest n value. Any other electrons in lower energy levels than that are considered part of the core electrons, and they have configurations that are similar to a noble gas. And because the noble gases are very stable, those inner core electrons for any atom are very stable. So the outer electrons, the valence electrons, will participate in all sorts of bonding and transfer and chemistry, whereas the inner core electrons don't. We generally can ignore them for most purposes when we're talking about the chemistry of an atom. Okay? So to think about that in terms of a specific example, we have here the electron configuration, right? And since the structure of the core electrons in any atom is just like the next smallest noble gas, that symbol can be used to abbreviate the core. Okay, so the core here, the red electrons, and then you have the green electrons, which are the valence. Okay, the green ones listed here are the valence electrons because they're in the highest energy level of n equals 3. Okay? All of the other electrons in this configuration are in lower energy levels, either n equals 2 or n equals 1. So these 2 electrons, which are in the 3s orbital, are the valence electrons. These electrons here, and you have 6 plus 2 plus 2 for a total of 10 core electrons, are the core, right? This core configuration is identical to the configuration of neon. And so we can replace that whole thing with the symbol for neon in square brackets like this. It's a way to abbreviate the electron configuration so that you don't have to write the whole thing out every time. So let's look through the whole periodic table, or the first few rows of the periodic table anyway, to see how this works in practice. Okay, so hydrogen, I've been saying, is atomic number 1. It has just a single proton, therefore only a single electron. That electron is going to go into the lowest energy orbital possible, which is a 1s orbital. Okay, so we write the electron configuration for hydrogen as 1s with a superscript 1 because it has a single electron in it. For helium, that same orbital gets a second electron because helium needs 2 electrons to be neutral. It has atomic number 2, 2 protons, requires 2 electrons for neutrality. So both electrons go into the 1s orbital, and therefore this number changes to a 2. So it's 1s2 is the configuration. At this point, the energy level n equals 1 is complete. There's no p sublevel, right? Because the n equals 1 energy level only has an s sublevel. So helium is the most stable of these first row elements, which is why, again, why it's over on the right side with the noble gases. Moving down to the second row, we see that we have lithium, which is atomic number 3, so we need to figure out a place for 3 electrons. We always start at the beginning, so the first 2 go into 1s as usual, and then the third goes into the 2s orbital. And so we can write it like this, 1s2, 2s1. But this 1s2 orbital is really just a filled n equals 1 energy level, which is the configuration of helium. So we can replace it with the symbol for helium. Okay? And in fact, all of the elements in this row have a filled 1s orbital. Right? They all start with 1s2. And so all of these can take helium as an abbreviation. We can start writing these all with helium to abbreviate the 1s2 orbital. Okay? At this point, the helium abbreviation doesn't really save us much in terms of how much we need to write, but later on in the next rows, we'll see that it can actually save quite a bit of writing. Okay. So here's the next row, right? N equals 3, the period 3 row in the periodic table. It begins with sodium, atomic number 11, so we have to figure out how we can fit 11 electrons into the orbitals. Okay, so this doesn't show, this is abbreviating already the orbital diagrams because it doesn't have enough room to show all of the blocks. But we can, I'll just draw it up here, right? So we start with the 1s orbital, and it gets 2 electrons. Then we have the 2s orbital, that also has 2 electrons, so that's a total of 4. Then the 2p orbital is 3, I'm sorry, the 2p sublevel is 3 orbitals, and they each get 2 electrons. Okay, and this now is the configuration of neon. Neon is atomic number 10. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in these levels that I've drawn up here. So this is neon. So to get the next element after neon, which is sodium, atomic number 11, you take this configuration and then you just add an extra electron to it. The extra electron has to go into the next highest energy level, which is n equals 3, and it's going to start, as every energy level does, with an s sublevel. So the 11th electron in sodium goes into the 3s orbital like you see here. And you just have to specify that neon is in front of it because it has the neon core configuration and then one additional 3s electron. Okay? So the configuration is written out completely here. Okay? And so I'm going to draw a box around the part that's neon, which corresponds to the orbital diagram that I drew up top. And then there's this additional 3s1 electron. It has 1 valence electron. Okay? These electrons that make up the neon configuration are the core electrons. This one is the valence electron, and so we can write it as neon with a 3s1 appended to it. For magnesium, it's pretty much the same, right? We can start with the neon core, And now we just need 2 additional electrons, and they're both going to go into the 3s orbital. So these are the 2 valence electrons, and we can write it like this. Okay? So sodium, which has 1 additional electron, is in the first group, and it has 1 valence electron. Magnesium, which has 2 electrons more than the previous noble gas, is in the second group, and it has 2 valence electrons. Okay? These numbers all match. They're all the same. They all indicate the same thing. Then we can jump across the gap and get over to the p block, and we would see that aluminum, which is atomic number 13, it fills up the 3s orbital, and then 1 electron has to go into the 3p orbital. Okay, so all 3 of these electrons are the valence electrons, and this is, again, neon. Okay. And then to go from there, we can see what happens when you add even more electrons to the sublevel. Remember, the electrons spread out as much as possible. So for silicon, if you have to put 1 more electron in, it goes into a separate orbital in the 3p sublevel. And then phosphorus, with 1 more electron, goes into yet another orbital within the 3p sublevel. And it's only after the 3p sublevel has 1 electron in each orbital that the next electron can double up. Okay, sulfur has a paired electron in the 3p orbital. Okay? But overall, sulfur here has 4 electrons in the 3p orbital. That's why this is 3p4 over here. It has 2 electrons in the s orbital, and that's why this is 3s2. So between the 2 electrons in the s orbital and the 4 electrons rather in the p orbital, it has a total of 6 valence electrons. Okay? It has the neon core and then 6 valence electrons. It's in group 16 or 6a. So again, you can see the number of valence electrons from the group number, and we'll get to that more later. Here we have some other periods, right? Period 4 and above, beginning with potassium and calcium. Potassium is back in the s block. It's in the first group because its last electron goes into an s orbital, the 4s orbital. So it really has the configuration of argon plus a 4s electron. Calcium has a configuration of argon and 2 electrons in the 4s orbital. Okay, so this has 1 valence electron for potassium and 2 valence electrons for calcium. In period 4, then we also have the d block. But remember, with the d block, the energy level is offset from the rho. So after the 4s orbital is filled, we go back to the 3d orbital. Okay, so we go from n equals 4 back to n equals 3 to fill up the d sublevel. And the d sublevel is, again, 5 orbitals, and each orbital can hold 2 electrons, so that's a total of 10 electrons, which is why the d block is 10 electrons wide. From scandium to zinc is 10 columns. So here we can see that scandium has the argon noble gas core and 2 4s electrons, and 1 3d electron. Okay. There's a couple of things in here where you have this throws off the order a little bit, because you can see that there's only a 1 electron in the 4s orbital here, and same thing here, there's only 1 electron in the 4s orbital. So these are exceptions to this general rule based on the quantum mechanics underlying this phenomenon, but you don't really have to remember this. You don't have to memorize the electron configurations for chromium and copper. Right, and then we have the period 4 p block, which starts at gallium and goes to krypton, and again, you're dealing with the argon noble gas core, argon being the previous noble gas in row 3, period 3, plus some additional n equals 4 electrons, and then also the 3d electrons that you need. So after you fill the 3d sublevel in the transition elements, then you go back to 4p. So this, again, is a lot of information that's a little bit overwhelming at first, but it really helps to do some examples. Okay, so we're going to look at the periodic table and using the periodic table to write out these electron configurations. So let's try it for an element Se, which is selenium. Okay, so the first thing you have to do if you want to write the electron configuration for an atom, you have to locate it on the periodic table. Okay, you have to know what its atomic number is. If you really memorize this stuff, then once you know the atomic number, you should be able to do it from there. But I'm not expecting anybody to do that. I'm not even sure that I could do that myself, right? I prefer to look at the periodic table to actually count through the different blocks. So selenium is here. It's period 4, group 6A. In the new system, it's group 16. Okay. In this periodic table, like some others, you might see the group numbers, the old group numbers, are written in Roman numerals. So 6A is written as 6A. VI is Roman numeral for 6, and then the A is after it. So 6A, right? This is 7A, this is 8A. So you need to get used to your Roman numerals a little bit. That'll also be useful in the next chapter. Okay. So selenium is in group 6A, period 4, and it is atomic number 34. That means we have to account for 34 electrons. We have to place 34 electrons into our orbital diagram. So to do that, the first thing you do is remember the sublevel blocks. And so here I've color-coded them, right? The S block is red. Helium is also red because it's technically part of the S block, even though it's over with the noble gases. The P block is green, okay? And the D block is this purple, violet color. And then you just count from left to right, top to bottom. So the first electron starting here is n equals 1, right? It's the first row, and it's in the S block. So it's an S orbital. 1 electron for hydrogen, and then a second electron for helium fills up the 1s orbital. So 1s2 gets you over to the helium configuration. Then you move down to the next row, right? After you filled up 1s2, n equals 1 is finished, and now you need to go to n equals 2. Well, that's the second row. And so we can start putting electrons in. The first 2 electrons go into the s orbital of the n equals 2 energy level. Okay? It's 2 columns wide, right? So lithium would be 2s1, beryllium would be 2s2. And then you can skip across and you would get boron, which would have a 2p1, 2p2 would be carbon, nitrogen is 2p3, oxygen is 2p4, fluorine is 2p5, and neon has a 2p6 configuration. Okay? So you're counting the number of elements that are in that block to tell you how many electrons go into that sublevel. There's 2 elements in the S block in row 2, so 2 electrons go in there. There's 6 elements in the P block in row 2, so 6 electrons go in there. Okay? At this point, we've accounted for 6 plus 2 plus 2, which is a total of 10 electrons. And not by coincidence, this has gotten us to atomic number 10. 10 electrons corresponds to an atomic number of 10. Right? And so we can continue. Next row, n equals 3. We start back at the S block, so we're filling a 3s orbital, and it has 2 columns, so we put 2 electrons in it. Then we can skip over to the 3p block and put in 6 electrons. Okay, so this is going to give us another 8 electrons on top of the 10 we already have, makes this atomic number 18. Okay, so far this has the configuration of argon. Okay, and in fact, you could even abbreviate this with the square brackets as the argon configuration. Okay, all the way up to 3p6 is the argon configuration. Keep in mind, we have not started filling the 3D sublevel yet. So after 3p, then we go down to the next row, right? So we're just going, again, left to right, top to bottom, across the periodic table and down the periodic table. So after you finish row 3, you go down to row 4. And row 4 means you're starting with n equals 4. And since you're, again, back in the S block, you're going to 4s. So there's no reason you should think that you've started filling the 3D orbitals yet, because we got through the whole third row without going into the D block, right? But after the 4s electrons are placed, this one and this one, then we get to scandium, which is where we have our first D electron. So here we have a 3D level, right? Remember, the transition elements, the n value is lower, 1 less than the row or the period. So it's row 4, period 4, but the D block is in n equals 3. Okay, so we're in the 3D block, and it's, again, 10 columns long. And so we have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so we can put 10 electrons into the 3D sublevel. Okay, and then we get to the P block, and we're almost there. We're almost to selenium. In fact, we're not going to complete another block, another sublevel. We only get to put in 4 electrons into this 4p block by the time we get to selenium. Okay, so again, we're going back to the p block. So our n value is going to once again match the row number, which is 4, but we're in the p block, so it's 4p, and we're counting 4 columns in to get to selenium. So this last sublevel, the 4p sublevel, only gets 4 electrons. It has room for 2 more, right? 1 more would put you at bromium, 2 more would put you at krypton, but we don't have those, we only have these. So at this point, we're done. And you can see that we've counted through the whole periodic table, and we have the electrons in the right configuration. Okay? Now again, with this configuration, there's a couple of things we can do. We can go all the way through the previous noble gas, right? So if we're at selenium, we can look backwards and find the previous noble gas, and it's argon, right? Krypton would be the next noble gas, but argon is the last noble gas before selenium. And so we can abbreviate through, argon is in the 3rd row, so we can abbreviate through the n equals 3 energy level in the p block with argon. So this whole part of the configuration here can be abbreviated as argon. And then we can put in the 4s2 electrons, the 3d10 electrons, and the 4p4 electrons. Okay. Another thing to notice about this is we counted all of the electrons as we were going, and we got to the final atomic number of 34. So if you add up all of these superscripts, you should get 34. Okay, so 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, right? So argon has 18 electrons. And then we have another 2 for 20. This is another 10, which gives us 30, and this is 4, which gives us 34. Okay? So 34, the atomic number, you can double check that by adding up the superscripts in your electron configuration. So let's look at another example. Use the periodic table to give the symbol and name for the element with the following electron configuration and identify the core and valence electrons. Okay, so let's do the first part, and then we'll identify the core and valence electrons. So first of all, how do we figure out what element this is? Well, there are 2 methods. One is if you get familiar with the different blocks in the periodic table, the S block, the P block, and the D block, then you can just look at which is the last sublevel in the electron configuration. Right? In this case, it's a 3D sublevel. And so you can find the D block and figure out which row corresponds to n equals 3. Just keep in mind it's going to be the 4th row because the D block is 1 less than the row number, the period number. So the period 4 transition elements correspond to the 3D sublevel. And we can see that there's 7 electrons in the 3D sublevel. And so we count in, starting at the first electron in the D block, which is this, 1, 2, 3, 4, 5, 6, 7. Right? And the 7th column in is cobalt. So this must be cobalt. So this is the first method that you can use to do it. Again, it requires you to remember the blocks a little bit, the S and the P and the D blocks a little bit, and know how to count that way. So there's a slight trick to it, but it's very simple to do it once you get used to it. The second method doesn't require you to remember the blocks really. It just takes a little bit more simple math, right? So you recall that the superscripts in the electron configuration correspond to how many electrons are in that sublevel. So you can just add up those numbers to figure out how many electrons are in this configuration. So we start with 2, another 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 7 is 27. Okay, so the total number of electrons indicated in this electron configuration is 27. Which means if this is a neutral atom, it has to have 27 protons. And if it has 27 protons, it must be atomic number 27. And if it's atomic number 27, it must be cobalt. Okay? So both of these methods really require you to have a periodic table in front of you, which is fine. You should always have access to a periodic table. There are plenty of apps you can put on your phone with periodic tables. You can print one out and sit it right next to your computer while you work. It's an invaluable tool in chemistry. It's something that you should always have and always be referring to. And it's not It's not a problem to use it. The issue is you need to know how to use it and to know how to interpret it according to the way the rows and the columns are arranged. Okay? It's not just arbitrary. The next part is figuring out which are the core and which are the valence electrons. So for this example, it's a little bit tricky. So the valence electrons are the easiest ones to figure out because they are the electrons that are in the highest energy level. And the highest energy level is the highest value of n. So in this entire configuration, this is the highest value of n equals 4. Okay, so you have a 4s sublevel, and it's got 2 electrons in it. So these 2 electrons in the 4s sublevel are the valence electrons. Okay, they're shown in green. The core electrons are the electrons that are in the fill. They're the central electrons in the lower energy levels, but really they're the electrons that have the same configuration as the noble gas. They're the ones that you would abbreviate with the noble gas symbol. So here we have a filled n equals 1 energy level, a filled n equals 2 energy level, and then the filled 3s and 3p energy levels, right? And that would bring you up to argon. So through here is the configuration for argon. Okay? So essentially you have an argon core plus these 2 electrons that are in the 4s orbital, and also some electrons, 7 electrons in the 3d orbital. So the electrons that are shown in red here are the argon core. Those are the core electrons. The ones in green are the valence electrons. And obviously you would then be asking, well, what's the deal with these d electrons? The 3d electrons are a little trickier to think about. They're not usually considered part of the valence electrons. And in this course, we're not going to count them as valence electrons. They are also not really counted in the core because they don't form a closed shell. They don't have a closed energy level or a completely filled energy level. So they're not part of the argon core. They're in addition to that. But they don't really contribute to bonding and chemistry in the same way that the highest energy level electrons do, in this case the 4s electrons. So we don't really need to consider them as much. The fact is, any element that has a partially filled d orbital, or even a completely filled d sublevel, is part of the transition elements. And their chemistry can be pretty complicated. They can form a lot of different types of ions and bonds and things like that. So it's not something we're really going to worry about too much in this course. So just keep in mind that we don't count d electrons as part of the valence electrons. Okay? So you just look at the highest energy level, and that will be your answer. In this case, n equals 4 has all of the valence electrons. Let's do a few more examples. Okay? So write the electron arrangement or the electron configuration for the following elements: carbon, silicon, and oxygen. Now, to do this, you need a periodic table. I'm not going to keep switching back and forth between the slides and the periodic table, so if you're following along, just get out a periodic table, maybe open it up in one of the other windows so that you can see it and refer to it, or better yet, have a printout next to you, because I'm going to assume that you're looking at the periodic table yourself, okay? But I'm not going to keep switching back and forth on here. So the first step is, again, locate the element in the periodic table. Carbon is atomic number 6. It's in period 2, group 4A, which is group 14, the 14th column from the left in the new numbering system. Silicon is actually right below it because it's also in group 14 or 4A. It's in the 3rd period, so it's in the row right below carbon, and its atomic number is 14. Oxygen is in the same row as carbon, okay, but it's 2 columns later. It's in column 16 or 6A, group 6A. And oxygen has an atomic number of 8. Okay? So the periods and groups here to help you locate it, but really what we need are these atomic numbers. So for carbon, we're going to need to place 6 electrons. For silicon, we're going to want to find a place for 14 electrons. And for oxygen, we're going to want to find a place for 8 electrons. So you can start filling the electrons according to the periodic table, right? So if you're past the first row, then you know that the first row is filled, and the first row is 1s. So all of these have a 1s2 at the beginning, okay? because all of them are second row or lower. Okay? They're also all in the p block. So if carbon is in the second period in the p block, then its 2s orbital must be filled. So the 2s orbital has 2 electrons. So carbon so far has 1s2, 2s2. Silicon also has 2s2. Oxygen has 2s2. Okay? Now silicon, in fact, is in the third period. So if we're doing silicon, we can fill in the entire n equals 2 energy level. So in addition to the 2s sublevel being filled, the 2p sublevel is also filled with 6 electrons. Okay? So at this point, we've accounted for 4 electrons for carbon. 2 plus 2 is 4, plus 6 is 10, plus 2 electrons here in the 3s. So that's 12 electrons accounted for with silicon, and again, 4 electrons accounted for with oxygen. Okay? So again, because silicon is in the p block of the third row, we can assume that the s block is filled in. So then we have to keep going, right? Carbon is in the p block of the second row. We finished the s block of the second row, so now we just have to count how many columns carbon is in the p block. And so if you count, it is 2 columns into the p block. So it has 2 electrons in the 2p sublevel. Right? At this point, we have 2 plus these last 2, and that equals 6 electrons. Carbon is atomic number 6, and so at this point we're done with carbon. I'm going to skip to oxygen to do that because it's basically the same, except oxygen is 4 columns into the 2p block. So instead of being 2p2, which would be carbon, it's 2 columns more, which means 2 more electrons. So 2 plus these 4 gives you 8 electrons. And since oxygen is atomic number 8, this is the complete configuration for oxygen. And then silicon, we saw that we filled the n equals 1 row, we filled the n equals 2 row, the second period, we filled the s block of the third period, and now we need to count into the p block of the third period, and it's 2 columns in, just like carbon is 2 columns in, silicon is right below it, so it's 2 columns in, or 2 electrons, but instead of being in the 2p, it's in the 3p sublevel. And so again, we have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus another 2 is 14 electrons. And silicon is atomic number 14, so this is the complete configuration for silicon.